Good morning. In this session, we are going to discuss the most commonly used controller, that is PID controller. In the last session, we have seen the individual control actions, that is proportional control action, derivative control action, and integral control action, and understood their physical significance and the individual merits and demerits of each one. So in this session, we'll combine the control actions and discuss the three widely used controllers, that is PD control, PI control, and finally PID controller. So let's revisit the closed loop control system where we have a plant. To this plant we'll give the input, or which is also called as the desired output, and the output from the plant is called as the actual output. So this actual output is fed back with the help of this feedback channel, and it is called as feedback signal. So this feedback signal will go to this comparison unit and will construct a error signal. The function of this controller is to minimize this error, and the output from the controller is known as actuating signal, and this actuating signal is going to drive the plant. So in other representation, the same closed loop control system can be shown as like this way, where RS represents the input, CS represents the output of the system. This is called as the transfer function of the plant. HS is called as the transfer function of the feedback signal. ES is called as the error signal, and EAS is called as the actuating signal, which is the output from the controller. Finally, this K is called as the controller gain. First of all, we are going to discuss the PD controller, in which the actuating signal is proportional to the error signal, and it is also proportional to the rate of change of error signal. So we have two inequality constants. To bring it into equality, we'll introduce two constants, so which means that EAT is equal to Kp times Et plus Kd times Det by dt, where Kp is called as the proportional gain and Kd is called as the derivative gain. Now if we take the Laplace transform of this equation, which gives us EAS is equal to Kp times ES plus Kd times, because it's a rate of change of error, so S into ES. So we can take ES common in this case, and we have EAS divided by ES is equal to Kp plus SKD. So this Kp plus SKD is called as the gain of the PD controller, which can be shown here like this. Next, we can see that the open loop transfer function for the PD controller is written as Kp plus SKD into omega n square upon S square plus 2 zeta omega ns, and Hs in this case is unity. So we can write the overall transfer function for this system as Cs by Rs, which is equal to Gs upon 1 plus Gs Hs, so which can be written as Kp plus Skd times omega n square upon S square plus 2 zeta omega ns divided by 1 plus Kp plus Skd times omega n square upon S square plus 2 zeta omega ns, so which can be equal to Kp plus Skd into omega n square upon S square plus 2 zeta omega ns plus Kp plus Skd times omega n square, so which can be further simplified. So this expression is called as the transfer function of the closed loop control system with using PD controller. Let's rewrite the transfer function of the PD controller as. Now if we compare it with the transfer function of the plant, which was given when the value of this k is 1, and the transfer function of the plant can be written as Cs by Rs omega n square upon s square plus 2 zeta omega ns plus omega n square. So if we compare the transfer function of the PD controller with the transfer function of the original plant, we can clearly see that there are three changes which the PD controller has brought into the transfer function of the original plant. So first of all, in the damping ratio, so that change, we can see that if we have to find out the damping ratio of the original plant, whatever is the coefficient of s in the denominator polynomial, if we divide 2 zeta omega n divided by 2 omega n, we can find out the value of zeta. The same thing we can do it with this term, which is the coefficient of s of the PD controller. So 2 zeta omega n plus kd omega n square divided by 2 omega n, which should give us the new damping value as zeta dash. So which gives us that zeta dash is equal to 2 zeta omega n divided by 2 omega n plus kd omega n square divided by 2 omega n. So which should give us, so this will cancel out, so zeta plus 1 omega will cancel out with this, so kd omega n divided by 2. So this is the value of the new damping, where we can clearly see that with the use of PD controller, the effective damping ratio of the system has increased, which will result in decreasing the overshoot value, because we know that the percent overshoot is equal to minus zeta pi upon 1 minus zeta square. So if zeta will increase, the percent overshoot will decrease. So that is the first thing that the PD controller has brought into the system. The second thing is, if you see, the original natural frequency of the system is omega n. The modified frequency of the system is equal to kp omega n square. So which means the natural frequency of the system has changed from omega n to under root kp omega n. And the third thing is that it has brought a 0 to the system. So that 0 is equal to s equal to minus kp by kd. Earlier in the system, you can see there is no s term in the numerator polynomial of the original plant. Now this term will introduce a 0 in the left half plane, so which will basically change the response of the system. So hence we can see, using PD controller, so there are three changes. So if we want to tune the damping ratio of the system, we can see that we should tune kd, and if we want to change the natural frequency of the system, we should play with the kp tuning parameter. The reverse is not true. So if you want to change the damping ratio of the system and you keep on tuning the kp parameter, it is not going to work. So next we are going to discuss the steady state error, which we know is given as es by rs is equal to 1 upon 1 plus gs hs, and we know that gs in this case is given as, and hs in this case is equal to unity. So if we plug in these values, so we can find out that the steady state error is equal to 1 upon 1 plus kp plus skd times omega n square upon s square plus 2 zeta omega ns into 1, and we can write this in simplified manner as s square plus 2 zeta omega ns upon s square plus 2 zeta omega ns plus kp plus skd times omega n square, which can be written in more simplified manner like this. And finally we know that the steady state error is equal to limit s goes to 0 s into es. So we can write this term as limit s goes to 0 s into Es we can write it as s plus 2 zeta omega n upon s square plus 2 zeta omega n plus kd omega n square s plus kp omega n square into rs. So this is the expression for steady state error, which we can now calculate for different inputs. So let's rewrite this steady state error as, now we'll take the first case where rs is equal to step input, which is written by 1 by s. So here we can see, so the ess, the limit s goes to 0. So with this whole expression, if we divide by 1 by s, so the 1s will cancel out with the 1s in the numerator polynomial, and still there is 1s in the numerator which is left, which will make this steady state error to go to 0. The next input as the ramp input, where the rs is equal to 1 by s square, so which leads to the steady state error as limit s goes to 0, this whole expression into 1 by s square. So 1 by s square will cancel out the two s terms in the numerator, so which will give us the value as 2 zeta omega n upon kp omega n square. So this term omega n will cancel with this, so the net result is 2 zeta by kp omega n. So that is the steady state error in the case of a ramp input, and here we can clearly see that the steady state error, there is no contribution from kd side, which we have concluded in the last session also, which means that the derivative controller has no bearing on the steady state error. So that also we can conclude from this expression. And third, we can see if the input is a parabolic input where rs is equal to 1 by s cube. So in this case we can see, so there is one s in the denominator that will be left, and which will make the steady state error to go to infinity. So which means that using a PD controller with parabolic input is a blunder mistake. Next, the observations which we can notice from the PD controller are, first of all, if we want to change the damping ratio of the closed loop system, we should tune KD. To tune the natural frequency of the system, we should use KP. And finally, to reduce the steady state error for ramp input, which was we have noted that the steady state error was given as 2 zeta by kp omega n. So if we want to reduce the steady state error, we should increase the value of kp, because this is the only tuning parameter which we have at hand. However, it is not possible to make the steady state error 0, because to make the steady state error we should increase the value of kp to infinity, which is practically impossible because kp is related to the torque being given by a motor, and in this real world no motor can give infinite torque. And finally, the added 0 in the numerator expression will modify the time response of the system. So these are the major changes which the PD controller will brought into the system. Next, let's try to see the effect of a PD controller using a graphical representation. Let's say we are having an error signal which is given like this way, where we can see that up to here there is no error, and beyond this point the error is continuously increasing. Now if we see the effect of only derivative controller on this error signal, which is rarely being used alone, so here you can see when there is no error in the system, the output from the PD controller is 0. Now, as the error keeps on increasing continuously with the constant slope, the PD controller will give constant value with an abrupt change at this instant where the error starts. So this is the derivative control. And if we see the effect of a PD controller on this error signal, where when there is no signal, the output from both proportional control as well as the derivative control is 0. Now as the error increases, so this is the contribution from derivative control, and the orange one is the contribution from proportional control, because as the error increases, the output from the proportional part of the PD control will keeps on increasing. So this is the contribution of individual component in the PD control to handle this kind of error signal. Next we will discuss the PI controller, which means that the actuating signal is proportional to the error signal as well as it is proportional to the integral of the error signal. Again, to break these two inequality constraints into equality constraints, we will introduce two constants, which is equal to kp into et plus ki into integration of et dt, where kp is called as the proportional gain and ki is called as the integral gain. Now if we write the above expression using Laplace transform, we can write that EAS is equal to kp times ES plus ki into ES divided by S. So if we take ES common and take on this side, so EAS divided by ES is equal to kp plus ki divided by S. So that is the transfer function using the PI controller, which is shown in this figure like this. So the overall transfer function of the PI controller is given as CS by RS is equal to kp plus ki by S into omega n square upon S square plus 2 zeta omega n S upon 1 plus kp plus ki by S into omega n square upon S square plus 2 zeta omega n S. So which can be simplified and can be written like this way, that CS by RS is equal to kps plus ki into omega n square upon S cube plus 2 zeta omega n S square plus kp omega n square S plus ki omega n square. Now here you can see, using the PI controller, the order of the system becomes 3, which can be clearly seen from this cubic polynomial in the denominator. So in this, the order of the system is 3. So which means that using PI controller, the order of the system has increased from second to third. So the denominator polynomial is also known as the characteristic equation, which will result in 3 roots. To ensure the stability of the plant, we can apply the Routh-Horvitz criteria, which states that if 2 zeta omega n is less than or equal to ki, the two roots have positive real part and the system is unstable, and whereas if the value of 2 zeta omega n is more than ki, all the roots have negative real parts and the system becomes stable. Next we will discuss the steady state error using PI controller, which can be written like 1 upon 1 plus kp plus ki omega n square upon S square S plus 2 zeta omega n, and finally ES can be written as S square S plus 2 zeta omega n upon S square plus 2 zeta omega n plus kp omega n square S plus ki omega n square into RS. And finally we can write the steady state error ESS as limit S goes to 0 S into E of S, which will give us S cube S plus 2 zeta omega n upon S square plus 2 zeta omega n plus kp omega n square S plus ki omega n square into RS. So this whole expression is under the limit S goes to 0. Next we can calculate this steady state error for different kinds of inputs. So let's rewrite this steady state error as, so let's take the first input as the step input, where we can see the RS value is given as 1 by S. So this 1 by S we can see will cancel the 1s term in the numerator polynomial. Still the resulting expression has 2s squares in the numerator polynomial, which will make the steady state error to go to 0. So whereas in the case of ramp input, where RS is equal to 1 by S square, still the steady state error is 0, because this 1 by s square will cancel only 2s in the numerator polynomial. Still there is one s pending, which will make the expression to go to 0. And if we compare it with the steady state error of this using PD controller, so the earlier expression was 2 zeta by kp omega n. Here using the PD controller with the ramp input, the steady state error was finite, which has been reduced to 0. So that is the biggest advantage of using the PI controller. And if we see the parabolic input, where the value of Rs is equal to 1 by s cube, the steady state error in this case is equal to 2 zeta omega n by ki omega n square, which omega n will cancel over here, so that leads to 2 zeta by ki omega n. And again, if we compare it with the steady state error of the PD controller, so which was infinity, so here we can clearly see that as compared to PD controller, the steady state error has been brought down from infinite to a finite value. So the observations from the PI controller are that it increases the type of the system, so type of the system has increased by 1. It reduces the steady state error of the system, as we have seen in the last slide, and finally it can counter the static loading. Finally, we can see the effect of a PI controller on the error signal, which is given like this way, where you can see up to this instance the error is 0, and then there is a sudden change in the error, abrupt change in the error, and then the error remains constant for rest of the time. So if we use only integral control, so in this case we can see that even in the portion where the error is 0, you can expect that the integral control will give non-zero value, because of which it can handle this constant static loading. And as the error signal becomes positive, then the integral control, which is based on the accumulation of the error, the output from the integral control will keep on increasing. And finally, the output from the PI control, which to this kind of error signal will be like this, where there is a constant error, then there is a constant jump from the proportional control, and there is a increasing output from the integral control. So this is the net effect of using the PI controller. We can compare the PD and PI controller based on the different types of inputs. So the first input is the step input, where the Laplace transform was 1 by s. The value of steady state error using PD control is 0. In PI control it is also 0. If we now come to ramp input, where the Laplace transform was given by 1 by s square, the steady state error using PD control was 2 zeta by kp omega n, which is a finite value, and this finite value has been reduced to 0 using PI control. And finally, if we are having a parabolic input where the Laplace transform is 1 by s cube, so using the PD control, the steady state error was infinite, which has been reduced to a finite value, which is equal to 2 zeta by ki omega n. Finally, we have the PD controller, where all the three control actions have been taken into account. So here you can see the controller is kp plus skd plus ki by s, and it will contain all the merits of all the three individual control actions. So in nutshell, we can say under the PID control, the proportional part of the controller will take care of the present state of the system. The integral part of the PID controller will take care of the past of the system, because it is based on the accumulation of the error. The derivative control action will take care of the future of the system, because it is anticipatory in nature. So in other words, the PID controller is like a famous Raj Kapoor movie, which is called as the Kal Aaj or Kal, where the integral control deals with yesterday, the proportional control deals with present, and the derivative control deals with tomorrow. So that's the crux of all the three control actions and their combinations. Thank you.